Okay, so we're moving on to chapter 3. So with that, in this chapter, we're going to be talking about sort of the sort of orbitals and how the atoms are held together within a molecule. So with that, the forces that and interactions that hold these atoms together are actually governed by quantum mechanics. And so with that, and one of those principles is the Heisenberg uncertainty principle. So with that, and that's really that leads to sort of help define the shape. So with that, but one of the problems with quantum mechanics is that you can't know simultaneously where a particle is, as well as where it's going, its momentum and stuff like that. But we can get a good guess and stuff like that by looking at sort of the probability of where an electron is around an atom, stuff like that. So that probability is called an orbital, and it's really another way of thinking about it is the electron density around the atom within the orbital, stuff like that. So the simplest of the orbitals is the 1s orbital. So all the s orbitals are spherical. There's sort of a electron density sort of going out from the electron or from the nucleus itself, stuff like that. So and so it's sort of so we sort of think of it as spherical shaped, like that. So So the other orbital that we're going to be talking about primarily in this course is going to be the p orbitals, and the simplest of the p orbitals is the 2p. So in here we've got sort of two phases, sort of like two lobes that are on either side of the nucleus. And they have sort of mathematical positive and negative values. Now that's different than positive and negative charges, but they have different values. One's positive, one's negative, and so how we end up mixing them is going to be having those positive and negative values is going to be a good chunk of this chapter, But one thing is the fact that with the s orbital, there actually is a lot of electron density near the nucleus. Here, in the p orbitals, there's actually no electron density at the node, at the nucleus, and that's what's called a node. So this right here, where there's no electron density, that's called a node. And so it has this sort of sort of dumbbell shaped like that, where these two have opposite phases. You can sort of think of it as opposite math. Sort of one is positively charged. One has positive values and negative values, but they have opposite phases. Okay, so about that. And the thing about the orbitals, right? So remember, there was three different types of orbitals. There's the px, the py, and the pz, right? So with the p orbitals, right? The px orbitals, those lobes go along the x-axis, and the py they go along the y, and then the z they look like that. So if you're going to put them all together, they would look like that. So with that, they sort of have this, almost looks like a bunch of grapes. So with that, sort of held together, or balloons or whatever, they're all taped together by their by their stem. So with that. So, but the rest of the s's and the rest of the p's all look like that. They're just larger, right? So with that, because they have to incorporate, they have to be able to, they have to accommodate those lower number orbitals. So the 2s, 3s, they're spherical, just larger, right? So 3p, 4p, they have nodes, or lobes, but they're just larger, stuff like that. But you can sort of think of it like that. Okay. Now the big thing is, how do these orbitals interact with each other? And so the way that they do this are what are called molecular orbitals. Okay, so for that, it's an interaction between these s and p orbitals that allow you to sort of make sense of all this sort of thing. And the first thing you have to think about is what's called constructive interference. Okay, so imagine you have a long rope, two people at the end. Okay, and they both shake it. Okay. So if they both shake it, so that, let's say both shakes go on that side, if they're going to travel together, when they hit the same spot, they're actually going to, get that hump's going to get bigger when they interact with each other, and then they're going to keep moving on, and stuff like that. And so this is constructive interference, meaning that when those two things come together, they're additive, all right? So with that, so they're constructive, so with that, things get bigger. So with that, the opposite change. So let's say they're opposite phases. Okay, so with that, so when they come together, they will deconstruct each other, right? So they'll negate each other, right? Stuff like that, and then they'll come back, stuff like that. So, again, if you want to think of these as the different parts as mathematical values, right? When you have two positive values, right? When you add those together, it gets larger. When you have a positive and negative, their sum is going to be less. That's all this is saying, stuff like that. Because what happens when you get two orbitals, you get this constructive and destructive interference, stuff like that. And so they're going to change their shape depending on where that is. Okay, so the way that this works is it turns out that a covalent bond, right? That's where two atoms are sharing the electrons. Okay, atomic orbitals can't handle that. The math associated with atomic orbitals doesn't work. Okay, but molecular orbital theory does. Okay, so because what we're going to have to do is we're going to have to take two atomic orbitals and overlap them. Okay, so you have what's called linear combinations of molecular orbitals, LCAOs. Okay, so in order to get this molecular orbital, you're going to have to combine the atomic orbitals within the atom. Okay, so let's say let's say you have a two atomic orbitals, right? So we're doing let's say a hydrogen molecule, right? So and so if they let's say they both have positive phases or positive mathematical values, right? When they add together, right, they're going to build up and have everything's going to be all happy. Okay, if you add a positive value and a negative value, or in positive and negative phases, when they come together, they're going to make this region here is going to be destructive interference, right? And then you're going to end up getting a node here. So this is what's called the bonding molecular orbital. This is what's called an anti-bonding molecular orbital. Okay, so like that. And so when you get bonding molecular orbitals, those are going to be the best. Okay, so that those are the lowest energy. So anti-bonding are going to be higher energy than the atomic orbitals, and non-bonding molecular orbitals are going to have the same energy as those atomic orbitals. So non-bonding is, we'll talk about this in a minute, but that's basically where you put lone pairs. Okay, so when you add these up, okay, so the number of orbitals that you put in is going to be equal to the number you get out of molecular orbitals that you get out. Okay, so you're going to put in the two the separate 1s orbitals from this hydrogen, right? And so out comes a bonding molecular orbital and an anti-bonding molecular orbital. Okay, this is what's called the HOMO. So with that, the highest occupied molecular orbital, right? Because it is highest occupied, right? So that it actually has electrons in it. And LUMO, this is the lowest unoccupied molecular orbital. So obviously it's unoccupied; it has no electrons within it. Okay, and when you're combining two orbitals or two s orbitals together to make a molecular orbital, the result that comes out is what's called a sigma bond. Okay, so that it's the Greek letter for S, right? So it has S character to it, so you're going to get a sigma bond. Okay. Okay, so how do we account for and so we talked in the last chapter about these this Vesper theory, so with that, and so how do we account for the bond angles? Okay, so with that, and the way that we do this is what's called hybridization. Okay, so with that, carbon or hydrogen's easy; it just only has one orbital that it can deal with. But with carbon, right, you have both the s and the p that you can that you have to work with, and you can actually combine them in different ratios. Okay, so if you take one of the s, right, so remember, carbon's going to have one s orbital. It's going to have, right, so with that, so if you do this, 1s, 2s, 2p, right, you can combine, and actually what ends up happening is you have these four orbitals, right, so that you can combine, right, the one from the 2s and three from the 2p orbitals. So if you just combine one of the s and one of the p, okay, you get an sp hybrid, right? So with that, and so let's say this s orbital has is positive phase, right? So with that, so if you put this on there, you get this side is going to be constructive, this side is going to be destructive, and so you end up with sort of this hybridized atomic orbital. Okay, so at that, and so you basically get a hump on one side. Okay, and depending on how the molecular orbital gets out, sort of how the p orbital is arranged, sometimes you'll have it on this side, right? Like that, and so you end up getting these little humps out. Okay, so like that, and so and don't forget, you can have the you can have it combined with the px or the py or the pz, right? So like that, but if you combine the s and the px, right, those lobes are going to be along the p orbital or the x-axis. If you combine the p or the py, the lobes are going to be along the y-axis. If you combine the pz with the s, those lobes are going to be along the z-axis. Okay, and what's going to end up happening is you're going to put one electron in each one of these lobes. So this side of the this sp orbital, one electron in the py, one electron in the pz, right? Because remember, there's 4 valence electrons in that carbon. Okay, so with that, and so with this one here, the other thing you can do is you can combine one of these with 2. Oh, I just said, notice that these 2 in the sp, you're only combining one of these and one of these. Okay, so that, so these 2 have been unchanged, right? So that means that like for this one, the px has been changed, okay, but the py and the pz remain unaffected. Okay, so if we come in here and we say, okay, we're going to combine 2 of these p orbitals and one of the s. So let's say we combine the x and the y, leave the p unaffected, right? It's going to look like this. All right, so, and again, notice how these are 120 degrees apart. Okay, so like that, but again, we're going to put an electron in each one of these lobes and then one in the pz orbital. Okay, 3 orbitals in, right? So with that, this one, and this one. So 3 lobes out, right? There, and there. So, and then this pz is unaffected. Okay, but again, you have that here. Because you have 2 of the p orbitals. You're starting to drop the amount of s character within the atom. Okay, now it's only 33%. For here, if you combine all 4 of these, right, now you only have 25% s character. But again, you get 4 orbitals in, 1, 2, 3, 4, right? You get 4 lobes out, 1, 2, 3, 4, right? And this shape is tetrahedral. So with that, so okay, so with that, so that makes perfect sense for what we're seeing in the Vesper theory in the previous chapter, right? So for sp, the bonds were 180 degrees apart. Okay, and it's linear geometry. sp2, the bonds were 120. It's a trigonal planar. That was the base structure, right? So with that, so if you have 2 groups, it's planar. 3 groups, it's trigonal planar. 4 groups, it's tetrahedron. That's the base structure, right? So with that, so this makes sense. So this is an sp. This is an sp2, sp3 hybrid system or atom. Okay, so so what about molecules beyond hydrogen? Okay, so with that, so valence bond theory, okay, atoms are bonded to 2 or more atoms. Atoms bonded to 2 or more atoms have to be hybrid. Okay, so with that, so hydrogen can get away because it just has the 1s. There's nothing to combine with it. Okay, but everything's basically going to be using its valence electrons in order to be able to get to the octet that's needed. Okay, so with that, so new orbitals are produced by mixing the atomic orbitals at a time. 2 atomic orbitals at a time, 1 from each adjacent atom, right? So with that, so what you're going to get is each one of, so this is an sp3, right? So with that, so this carbon, right, it's got 1, 2, 3, 4 lobes. That carbon, right, it's got 4 valence electrons, so it's going to put 1 electron in each one of these lobes, right? So this s orbital, right, from the hydrogens, it only has 1 valence electron, so it's going to take one from this lobe, 1 from the s orbital. That's going to be your bond. Same for this one. For here, again, you're going to put 1 electron into each one of these lobes, okay, for the 4 valence electrons in the carbon, right? So this valence, the valence electron from this lobe, the valence electron from that lobe are going to get shared between those 2 carbons. That's going to make, those are the 2 electrons for the bond. Okay. So if you're going to combine either, say, 2 s orbitals, 2 hybrid orbitals, or a hybrid and an s, those are always going to be what's called a sigma bond. Okay, so with that, and so what ends up happening is you get the so anything with s character to it is you're going to get a bonding. Technically, you're going to get a bonding and an anti-bonding. Okay, but we really don't care too much about the anti-bonding, right? Stuff like that. But for here, we put in 7 atomic orbitals. Okay, 4 from here, 4. What was it? 4. 4 from here. That's what 8, 9, 10, 11, 12, 13, 14. Okay, so you're going to get 7 bonding molecular orbitals and 7 anti-bonding molecular orbitals. Okay, so about that, and so, but here's where things, that's going to be the lowest energy, so that's where the atom's going to want to go. Okay, the problem comes is, let's say, so this is great for making a single bond, okay, carbon-carbon single bond, but we know that there's double and triple bonds as well. So how do we make those? Well, over there is what we need to do is we need to take the unhybridized orbitals. Okay, so here we're going to take, say, an sp2 where you only have the 3 lobes, right? But that in this case, sort of like the py has been unaffected. Okay, and what can happen is you take one of these p orbitals, and it only has 1 electron in it. You take across these 2 lobes. Okay, across these 2 lobes of the p orbital. Okay, it only has 1 electron. But notice how you're getting constructive interference here and constructive interference here. Stuff like that. And so what you can do is you can take the 2 electrons and smear them across here. And so this first bond that gets laid down between the 2 hybrids is going to be a sigma bond. And then you can put a another set of electrons in these p orbitals, stuff like that, to make a second bond across here. Okay, so each additional bond beyond a single bond is going to be a pi bond. Okay, so you can get it either constructive, right, to make the pi molecular orbital. You can get a destructive interference and to get the anti-bonding, right? So with that, so molecular orbital. Okay, so with that, now you do get, you know, pi and pi star, stuff like that. But these are going to be lower, sort of lower energy, right? So sigma bonds are going to be the lowest and the highest, or the sigma is going to be the lowest and the highest. With that, but the pi bonds are going to be sort of in the middle, right? So with that, and so your bonding is still going to be lower, but it's not going to be as low as the sigma. Okay, your pi, you know, for the symmetry, right? So the pi anti-bonding is still going to be higher than, you know, a non-bonding or whatever than the original, but it's not going to be as high as the sigma anti-bonding. All right, so with that, so not as much energy down, but not as much energy up as well. With that, so. Okay, so with that, so these have better overlap. Okay, so with that, than these. So with that, and so there's not as much energy needed to. So because you have good overlap here, you get a lot of energy out when you make the bond, which gives it the very high. If you can, you know, because of conservation of energy, if you drop a lot down here, that means you have to raise way up on the other end. Okay, here you're not getting nearly as good of overlap, so the drop isn't nearly as far. That means going up doesn't need to be as high. Okay, so with that, so for non-bonding, okay, I don't think, do we talk about triple? Oh yeah, we talk about triple bonds. Non-bonding orbitals. Okay, so that's where you have here, right? So with that, so you have formaldehyde here on this oxygen atom here, right? So with that, those two those lone pairs, that's where those go into what are called non-bonding orbitals. Okay, there's no overlap with other orbitals. It doesn't need them, right? It has its 2 electrons within that orbital. You know, you couldn't shove extra electrons within there with that. So, okay, so if you're going to make a triple bond, right? So with that, so now you've got sp, right? So you only have 2 lobes, right? So the 2 remaining p orbitals, you can get constructive interference between the 2. So they're sort of perpendicular to each other. So if one p orbital bond is like this, the other one is like this. It's sort of sticking out 90 degrees. I think the technical term is orthogonal, stuff like that. But it would be like this. So with that, so again, you get this sigma bond here between the hybrid orbitals. Okay, but you get the second bond that goes on is a pi bond, and then this third bond between these green p orbitals, that's going to be your that's going to be an additional pi bond because we're working with p orbitals. Okay, if you so a pi bond is only between p orbitals. Okay, they only have p character to them, and so that's where you get the p from, or that's where you get the pi from. So with that, because it's the Greek p. So with that, so okay, so again, the triple bonds, same deal. So you get Pi molecular orbitals, you get pi antibonding, pi bonding. They're not as energetic going down, so they don't need to be. The antibonding doesn't need to be as energetic going up. Okay, so how do you count these? Okay, so how do you count the bond, the sigma and the pi bonds? Okay, so with that, and so for here, right? So with that, so what ends up happening is every bond is always going to have one sigma. Okay, one sigma, one sigma, one sigma. Okay, now each additional bond beyond that first one is going to be a pi, right? So there's the sigma. Okay, so here's the sigma, right? And so that means these two right here, right? Those are 2 pi bonds. Okay. Here we have one sigma, right? But there's no additional bonds between these 2 carbons, right? No additional bonds. So in this case, there's 0 pi bonds. Okay. So for here, this one of these is going to be a sigma, right? Each additional one beyond that, so say this one, right? That's going to be 1 pi bond. Okay, so we have a triple bond, so we have one bond, or 1 sigma, 2 pi, right? So if you add that up, it's 3. Right here, we only have a single bond, so you have 1 sigma, 0 pi, right? So 1 bond. Here, we have a double bond, right? So with that, we have 1 sigma and 1 pi, so you add that up, it's 2, right? So it's a double bond. Okay. So there we go. Okay, so for determining hybridization, okay, the easiest way to do this is to think about letters. Okay, so with that, and so remember we talked about the groups in in Vesper theory. Okay, so let's say you have CH3. Okay, so let's say we look at that one. Okay, so what you're looking at, right, is lone pair sets. Oops, sets plus bond sets, right? And just like in Vesper theory, right, a single, a double, and a triple bond, those are all considered a set. Okay, so with that, and so for there, you're going to get out the number of letters that you need, number of letters. Okay, and so let's say right here. Okay, so we have, right, so here, how many groups do we have? We have 1, 2, 3, 4 groups. Okay, so we need 4 letters. Okay, so you start off with S, and then you need P, P, P. 1, 2, 3, 4. 4 letters, right? So that means this is an SP3. Okay, so this one down here, right? So it looks like. So you're looking at that carbon, right? So with that, so it has, right, 1, 2, 3 groups around it. Right, so with that, so 3 groups, so that means we need 3 letters. So you start S, P, P. Okay, so that means it's an SP2. Okay, so with that, and so for this one, right, again, we're looking at that. When we're looking at that oxygen, right, it has 2 bond sets. Okay, and then 2 sets of lone pairs, right? So it needs 4 letters, right? So with that, so it needs to be S, P, P, P. So it's an SP3. There you go. Not too bad. Okay. Okay, so we want to look at this. Okay, so this oxygen here, right? It has 1, 2, 3 groups around it, right? So 3 groups, so we're going to need 3 letters. So it's going to be S, P, P. Start with S and then add P's until you get all the letters you need, right? So this means it's an SP2. This guy here, right? So with that, it has 1, 2, 3 groups around it, right? So it needs 3 letters. So that one is also SPP, right? SP2. There we go. This one here, right? There's only 1, 2 groups around it, right? So that means you just need SP, or if you another way you put it, SP1. Either way. Okay, not too bad. It's not going to go any more than 3, SP3. So for that for carbon. Okay, so one thing that does happen is with free rotation. Okay, and you can take a look at this in your model set. Okay, so if you have your model set here, okay, you just have a carbon-carbon single bond there. Okay, within the model set, right, you can get free rotation around there. It's not a big deal. Okay, the model set does it. Because all you're dealing with is that sigma bond. So if you only have a sigma bond here, you can get this free rotation. If you just have a single bond, free rotation, no problem. Okay, but for the double and triple bonds, okay, you can't get rotation, right? So if you do, right, you're going to probably break your model set. Okay, and the reason why is if you were to try to rotate this, what ends up happening is those p orbitals that have to be aligned like this, as they're bent out of there, what do you have to do? You're breaking that interaction between those p orbitals, right? Now you're breaking the bond. You're literally breaking the bond. Okay, and stuff like that, and so we can't do that for rotation, so it's stuck. Okay, so carbon-carbon single bonds, free rotation. Double and triple bonds, can't get it. Right? You can't get free rotation on there. They are locked into place. Okay, and so what ends up happening is these molecules here. Notice it's kind of hard to see. You know, maybe you can sort of see it with the model kit or whatever. But these 6 atoms, this one, this one, this one, this one, this one, this one, those are all sort of locked in a plane, right? So like that, so you can sort of see they're all in a plane, something like that. So those ones around there. Now, if you had, say, like this one here, right, you can still get free rotation around that bond, okay? But you can't get free rotation around these guys. This guy here is held into place, but you can still get rotation around it, stuff like that. So, okay, so one of the things that happens with this, because you can't get free rotation around the double bond, okay, it's locked into this particular position, okay. So with that, and so let's say these two are chlorine atoms, okay. These guys here are locked. They can't get down there without breaking the bond, okay. And so when they are, so what's in this position is what's called cis, and when they are like this, they're called trans. Now, the only way you can get this is if you have a hydrogen on each side, okay, and then groups coming off of here, different non-hydrogens on here and here, okay. And so, because there's always going to be 2 hydrogens on here, that's what I always look at. People always look at this group and that group, whatever. But with cis and trans, you have to have 1 hydrogen on one side, 1 hydrogen on the other, okay. And so, what the deal is to take a look at where these hydrogens are pointing, okay. And so, if these hydrogens, right, the way that it's pointing away from the double bond, if one's up, one's down, like this, okay, one's going this way, one's pointed this way, they're opposite, and so that's trans, okay. But if they're pointed in the same direction away from the double bond, here and here, right, so with that's called cis, okay. So it doesn't matter if it's like this or like this, these are both cis bonds, okay. Now it makes a difference, right, so with that, to the interaction of the molecule, right, so cis 1,2-dichloroethene. This version, the cis version, has a boiling point of 63. This one has a boiling point of 47. Right. So with that, so it does make a difference even between the molecules. They have the same, molecular mass, right? But the way that the atoms are arranged in space is a little different. So that gives them slightly different boiling points. Okay. And this also has importance in nutrition. Okay. So with that, when we talk about fats, so with that, and so you talk about saturated fats. Stuff like that. So these are like your Crisco's and your solid fats or whatever, butter and whatnot. Okay, what saturated means is that you only have carbon-carbon single bonds in your chain. Okay, so that means that's what that refers to. When it's unsaturated, that means that it has a carbon-carbon double bond somewhere within it. Okay, so with that, and almost exclusively in biology, they like having these cis double bonds. There's some exceptions, but for the most part, it's going to be cis double bonds, okay, and stuff like that. And so if you get some sort of like soybean oil or corn oil or whatever, vegetable oil, whatever, it's going to have it's saturated. If it's monounsaturated, that means it only has 1 double bond. And if it's polyunsaturated, that means it has multiple double bonds within the chain, okay. And so one of the reasons why saturated fats are typically solids, but the unsaturated is typically liquids. Is how they pack, okay. And so the visual that I like to think about is if you have a bunch of people, like a large crowd waiting for a subway, Okay, they're on the subway platform. There's a whole bunch of them. Everybody's standing up straight, right? You can pack a lot of people in there if everybody's standing up straight, and you can sort of see this within the molecule that it can pack very straight. And so, because you can pack so many in there, it has a high high density. You have a lot of interactions, and so you can make it solid. Okay, but for here, this one actually has two. This would be a polyunsaturated, right? Because it has two double bonds in it. And notice how when you get a cis double bond, you get a kink in it. Okay, so with that, and this double bond kinks it back, right? So with that, and so what ends up happening is, now imagine trying to get all those people in there. If everybody has a heavy backpack, and everybody's sort of kinked over, you're not. They take up more space, right? And so you're going to have fewer interactions. You're going to be able to put fewer people on that platform, right? So with that, that makes it your fewer interactions. You're going to have. It's going to end up being liquid. So with that, because they just take up more space, and they take up, sort of because they're bent. Okay, now, and so what you do is if you want to go from here to here, right? There's actually a chemical reaction called a hydrogenation. So you talk about hydrogenated oils. What's happened is you've taken the double bond into a single bond, a carbon-carbon double bond into a single bond by adding hydrogens across it. Now, if this reaction goes poorly, one of the byproducts are what are called these. It actually reverts back to here, back to a level of unsaturation, but instead of going to a cis double bond, it goes to a trans double bond. Okay, and so your body's pretty good about being able to metabolize the unsaturated oils. It can, in some ways, metabolize these here, although not nearly as well. It really doesn't know what to do with these trans oils, stuff like that, and so these sort of build up, stuff like that. But but one of the things you're going to want to do, right, stuff like that, and so these actually they're not lethal, but they're much less healthy for you than even the saturated fats. Okay, so you really want to try to keep these out of your products, or out of your foods, stuff like that. So avoid products with them. Okay, it's molecular model kits, stuff like that, and so come in there and I would advise you, if you get one, to go in and play with it, to build the molecules. Certainly, one of these you can do is pre-build some of the molecules before you come into a test. You don't have to take time during the exam to build them and stuff like that. But get in there and learn how to work them. Learn how to make single bonds. Learn how to make double bonds. Learn how to make rings. The double bonds are usually the most difficult to be able to make. That's usually where people have the most problems, stuff like that. So learn how to do that. If you want to swing by my office, if you want to bring your kit in, I'll show you how to work it, stuff like that. So I've been doing this long enough that I kind of know what's going on with them, stuff like that. So, okay. Now with hybridization and bond characters, right? We talked about this in exam 1, right? Stuff like that. So the more sort of the more bonds you put in between two atoms, right, the shorter that bond, right? So a single bond carbon-carbon single bond is going to be the longest. The triple bond is going to be the shortest. Okay, long to short. Okay. Another way of thinking about this is the more S character you have in that in the hybrid atom, right? So that the shorter that bond is going to be. Okay, so you can even see that with the carbon-hydrogen bond here. The more S character there is on that carbon, okay, the shorter the bond is going to be. Okay, now the stronger it's going to be, something like that. But that's different than reactivity. Okay, so with that increase in character, shorter bonds. Okay. Now, one of the effects of this is the fact that as you pile in more electron density within two atoms. Okay, so that from carbon-carbon, so you have carbon-carbon single bond, you only have 2 electrons here. Double bond, you have 4. A triple bond, you have 6. Okay, as you start to build that up, you're starting to get more and more negative character within that, between those carbons. And so even though it's technically a covalent bond, right, you're between 2 carbon atoms with the same electronegativity, you're starting to build up negative character in there, and then that can go and attack things that have positive character, and that's going to be the basis for a lot of what the chemistry that we do in this course is going to be. Negatives coming in and attacking positives, even if they're partial negatives or partial positives. That's a lot of the driving force for these reactions. Okay, stuff like that. So okay, stuff like that. Good luck.